Welcome to next section of Unit 5. In photochemistry, the chemical reaction is carried out in presence of light. So, in this case, we have to find what is the rate of a reaction. Normally, thermal reaction, we find the rate of reaction, we find the efficiency of a reaction by rate of a reaction. In photochemistry, there is one term which explains the efficiency of photochemical reaction, that is quantum yield. Otherwise, it is called as a quantum efficiency. Here, what is the light is absorbed, how quantity of product is formed. This ratio is explained by quantum yield or quantum efficiency. This ratio actually number of molecules reacted or formed during the reaction in a given time period, that is equal, that is number of molecules reacted or formed in a given time divided by number of quanta or photons absorbed in the same reaction. When you think about the quanta, number of Einstein, one quantum is 1 Einstein. So, this ratio tells about the quantum efficiency of a reaction. According to Stokes-Einstein law, each molecule absorb one quantum of energy and each molecule absorb one quantum of energy and produce the product. This is the concept of this Stokes-Einstein law. So, for a reaction, the yield, that is quantum yield, is equal to 1 if it is one molecule absorb one quantum of energy. So, quantum yield is definitely 1 if Stokes-Einstein law, quantum yield is definitely 1 if the concept of Stokes-Einstein law is followed. But in experimental, we find that the yield of any reaction is not exactly 1, but it vary in different range. For example, we have decomposition of hydrogen peroxide and forms the product hydrogen and oxygen. We pass this energy. The quantum yield of a reaction is 2. Now, one more example, the formation of hydrogen bromide by reaction of hydrogen and bromine, we find that quantum yield is 0.01. And in one more case, hydrogen and chlorine react together and form 2HCl, hydrogen chloride formation. Here the quantum yield is 10 power 5. We observe that the quantum yield is not exactly 1. It varies from very minimum integer, minimum value, maximum value, even some point value is also there. This shows that there is some, it needs some explanation why the yield is, quantum yield is not 1. For this, we have some explanation. That is, quantum yield is not equal to 1. This is because of some understanding we have. What are all the concepts? Why this molecule show different quantum yield? If your molecule to produce quantum yield 1, there must be some conditions. What are all the conditions? That is, all molecules should equal in energy to produce equal number of molecules in the activated state and equal number of product formation. That is first condition. If it is happened, the quantum yield is 1. The reactivity should not depend on the temperature, because we find that some reactions are exothermic and some reactions are endothermic. So, the temperature variation around the molecule will not produce any change. Then, this is the second condition. Third one, the activated molecule should readily decompose to yield the product. That much of efficiency should need for the activated molecule. The fourth one, reactant should attain activated state readily after absorption of the light. So, if it is happen all these things in a molecule during the photochemical reaction, the yield of a reaction may be 1. But we find that many variation in the yield we have some reason why the quantum yield of a particular reaction is very high, why some molecule, some photochemical reaction has a low quantum yield. First we see the reason for high quantum yield. The absorbance of a light will lead to form an atom, activated atom, activated molecule, free radical. These are all under activated state, and this have a sufficient energy, or this activated molecule can propagate chain reaction. This activated molecule should propagate or must have a capacity to produce chain reaction. Then if a reaction have this, if a reaction produce this activated molecule, the quantum yield of a particular reaction is very high. The second reason, the intermediate state act as a catalyst. For example, if a reactant is there, intermediate is there and product is there. This is the energy level diagram. The reactant moves to activated state and which leads to product, and this intermediate state may act as a catalyst, or it may have some energy. It must have some energy that leads further. The second point is that the intermediate must have a capacity to propagate the reaction, or it may act as a catalyst. The third point, the efficient collision is the reason for a high quantum yield. If activated two molecules, two atoms are undergoing efficient collision, then there must be product formation. If the collision is not efficient, then there must be a reduction in the quantum yield. That's what we see in the next heading. Reason for low quantum yield. The activated molecule get deactivated before product formation. So this may be the reason for a low quantum yield. Second one, inefficient collision. How inefficient collision is happen? The activated molecule may collide with another activated molecule, means the collision is efficient one, it definitely leads to product. But if the activated compound is not collide with another activated compound, instead of that the activator is collide with unactivated, means the energy is transferred or energy is drained and it is not sufficient to carry out the product formation. This may be the reason for the low quantum yield. The third point, it may not obtain sufficient energy, which may not, the reactant molecule which absorb the energy, that is not sufficient to produce an activator molecule or free radical which further propagate the reaction, propagate the chain reaction. So the insufficient energy may be the reason for the low quantum yield. The final one, the activated state reverse to reaction instead of product formation. So the activated state must have a sufficient energy to produce product. Otherwise, the activated state molecule may deactivated or get reversed to reactant side. This also may be the one of the reason for low quantum yield. So all these things that explains rate of a reaction or efficiency of a photochemical reaction. Next we are going to see the photosensitization and quenching in photochemical process. What is photosensitization? We know that for a photochemical reaction, the product formation is only because of absorption of the light. If there is no absorption, no product formation. We find that many of the reaction is very important, but it is not carried out under photochemical process. This is because of inefficiency of a reactant molecule to absorb the light. So what is the solution for that one? In that, we are adding a foreign material or any substance that makes the reactant molecule to undergo photochemical reaction. How it is happen? This is the mechanism. This is the energy level of sensitizer, which is also called as a donor, And reactant, this is the energy level diagram for the reactant, which is also called as a acceptor. So when you think about the ground state, this is the ground state of sensitizer molecule. This is the singlet energy level of the sensitizer molecule. It is a triplet energy state of a sensitizer molecule. What is meaning for singlet and triplet? If an electron which exists in the plus half of rotation, it is moved to the excited state in the same sign, then it is called singlet state. If the electron change its mode of rotation, that is the sign of electron rotation is minus half, then it is called triplet state. The movement of an electron from the ground state to excited state, definitely first singlet state, then there is a possibility for the triplet state. But the direct movement of direct transition of electron from singlet to triplet is forbidden one. So now the given energy is absorbed by the sensitizer and there is an energy transition. Electron moves from ground state to excited state, and sensitive molecule have a capacity to undergo singlet to triplet state transition. This is called as a inter-system crossing, and this state and this under this at the time of in this energy state, in this triplet state, the molecule undergo de-excitation. This de-excited energy, which is in the form of light, is transferred to your reactant molecule, and this energy is and there is an energy match between this energy and the energy gap of a reactant molecule. So the released energy is sufficient for the molecule, for the reactant molecule to undergo activation. So here the absorbed energy of sensitizer is donated to reactant molecule to undergo reaction. This foreign material is called as a sensitizer. Here the photo energy is transferred, so it is called photosensitizer, and the process is called photosensitization. Many of examples we have. For example, we want to divide the hydrogen molecule under photochemical process. In normal mode, it definitely will not happen. Now, if we have a mercury in that, this mercury acts as a photosensitizer. Initially, it absorbs the energy and it is get activated. This activated energy is supplied to hydrogen molecule to form activated hydrogen molecule. This activated hydrogen molecule undergo dissociation and form atomic hydrogen. So, this is the one example of photosensitization. Another example is photosynthesis. Here the chlorophyll is act as a sensitizer. So these are all explain the photosensitizer principle and photosensitization process. The next topic is chemoluminescence. Chemoluminescence means during a chemical reaction, energy is released, and here the energy is in the form of light. Then it is called the light energy, light emitting process is called as a chemiluminescence. We can observe this process under the depth part of the sea. While we are going very deepest part of the ocean, there is also some plants are there which undergo food preparation. Without sunlight, how these plants prepare food? These plants get this light energy that is given by some chemical reaction that happen around the molecule which emit the light, and that light is utilized by the plant which present in the very deepest part of the sea area. So that plants are called chemoautotropes. The plants which is in the ground of earth takes photo energy from sun and do the food preparation. In that case, that plant is called photoautotrophs, and the plant which can't get the solar energy and get light energy that is emitted during the chemical reaction around the plants and do the food preparation, these plants are called hemoautotrophs. The next heading is bioluminescence. The same light is emitted in the biological material. For example, living organisms emit light energy, visible light, as a result of chemical reaction, then it is called bioluminescence. Example for one is fireflies and some marine animals, jellyfish, which produce light due to the chemical reaction that happen around the biological surface. This is called as a bioluminescence. So all these things are under the concept of photochemistry. The next heading is Jablonski diagram. Jablonski diagram that explain all the photochemical process. Here we consider this is the ground state of a molecule. That is called singlet ground state. As I explained, if a electron in the positive half, then it is moves to the higher energy level with the same spin, then it is called higher singlet state. So it is a singlet, first excited singlet state, this is second excited singlet state. There is more possibility of a molecule that moves from ground state to second level and third level, but the quantity of the transition quantity of atoms moves from ground state to second excited state is very minimum. The most probability of transition is singlet ground state to first excited singlet state. So if a molecule moves to second excited state, first it initially do internal conversion process, that is it is moves to the lowest excited state. That is, if a molecule in the second excited state means it moves to first excited state. If a molecule in the third excited state means it moves to the first excited state. So this process, this is also de-excitation process. It is called as an internal conversion. And if a molecule do a photochemical process, that is movement of an electron from singlet excited state to triplet state. This means the electron change its sign, then it is called inter-system crossing. Okay, so inter-system crossing means what? The electron transfer from singlet to triplet state. This is the another photochemical process. Now we come to the singlet state. If a molecule absorbs the energy and moves to the highest excited state, the first process is internal conversion. Now the elements or ions in the electron in the first singlet state. Here it has a two choice, either it have to undergo inter-system crossing or it have to undergo de-excitation process, that is movement of electron from the excited state to ground state, transfer of electron from the excited state to ground state. This happen in two ways. Either the absorbed energy is emitted in the form of released in the form of heat, or it may be emitted in the form of light. If it emits light during the de-excitation process, it is called fluorescence. It is a very short term one, so the lifetime of fluorescence is 10 power minus 8 nanoseconds. Then the second one is, if an electron in the triplet state, this electron may undergo de-excitation process, that is transfer of electron from the triplet state to ground state, and this also happen with the emission of light It is a forbidden one, so it takes long duration, and this process is called phosphorescence. So you can observe the light emission in a phosphor material after some duration, like even 1 minute, you can observe the light. So it is called delayed emission. It is called delayed emission. So the Jablonski diagram explains all the photochemical process. The next topic is Beer's law. It is one of a photochemical law that explains what is the correlation between the light absorbed and the concentration of the absorbing medium. Now we have to go. Now we are going in. We first read the Beer's law. When a beam of monochromatic radiation is passed through a solution, rate of decrease in the intensity of radiation with the thickness of absorbing solution is proportional to intensity of incident radiation as well as the concentration of the solution. So what is the thing that explained in the principle? If light is passed into the monochromator, we can get monochromatic radiation. This monochromatic radiation is fall on the sample. So initially it is called incident radiation. The molecule absorb the light energy. So due to that, the intensity of the outcome light is somewhat low. That is called as a transmitted light. What is the correlation between the incident light, transmitted light, and the concentration and the path length, the light travel in the absorbing medium? So we correlate all these things by Beer-Lambert's law. Beer-Lambert's law. So we observed that the decrease in the intensity or decrease in the transmitted light with respect to the path length is directly proportional to the intensity of incident radiation and concentration of the medium. Now we are solving this equation by doing some mathematical terms. So first we take that integration, that is I naught, initial radiation and transmitted radiation. Integral of I naught to I di by I, which is equal to minus kc integration of 0 to x into dx. After doing integration, we can have the ln I by I naught equal to minus kcx. Here k is nothing but molar absorption coefficient. Here when you remove the ln with the log, you must multiply with the 2.303 into log of I by I naught is equal to minus k into cx. If 2.303 is move opposite sides of equation, it becomes divide. So log I by I naught equal to minus k by 2.303 into cx. This is the total constant value. So it is put epsilon. Epsilon is nothing but molar absorptivity or molar extension coefficient. So absorption, log I by I naught is nothing but absorption. Absorption equal to epsilon cx. So by doing this experiment, we can find the unknown solution concentration. For example, if you have a iron solution, we prepare standard iron solution like 2 ppm, 4 ppm, 6 ppm and 8 ppm and 10 ppm. And we have a definite absorption for each concentration. So for each concentration we draw a graph, concentration versus absorbance. Concentration versus absorption. We find a graph that is steady line. If you have an unknown sample, for unknown sample you have only absorption. So from the standard graph, you draw a absorption line, and where it is cut, that gives the concentration of a unknown sample solution. So this is the one of application of Beer-Lambert's law. That is what we done in the doing in the spectrophotometer studies. So up to that I explained all the law under photochemical process and the concepts under the photochemical process. Thank you.